Greetings and welcome to another VMBlock screencast. In this screencast, we're going to continue with how YAWL handles storage. And in particular, what we're going to look at is how we can update a value in storage that is packed into a single slot. So if you take a look at this contract here, you can see that we've got a number of variables. And I know that these are all packed into the same slot, slot 3 of this contract. So we have 0 slot is this value, 1, 2, and then 3. All of these values are packed into the same slot. And we can see that in the contract if we call one of the functions below. So let's take a look at one of these functions here. Let's call get value by slot index, right? So if we deploy this contract and we expand and we call get value by slot index and we pass in slot 3, we can see that we get this number back, this large 32-byte number. And what you're looking at here, actually if I just copy and paste this up to this portion of the code, what we're looking at are all of these values packed into this single word. So we start off with the 9 over here on the right side, and then 128 bits later we've got the 7, and then the 5 here, and then the 5 is here, and then 3 and 2, and the 2 and the 3 are packed really tightly right at the end because they're both only 1 byte. So that's the contents of slot 3. Now the challenge is how can we actually update, say, this value here right in the middle. We want to update this value of C, which is currently 5. Let's say we want to update this to 10, and we want to use YAWL to do that. Well, firstly, I just want to show you that if you just use the old simple method, which is to update a slot with a new value. So we've got, for example, this function here, set value by slot index and val. I can pass in the slot index of 3 and the new value. So let me just show you, first of all, that I've got these values here. Let's just show you that the values are coming back as expected because we're calling the public getter functions of these variables by calling the values here. But if I set the value, so I use this function here and I pass in slot 3 and let's say 10, and I call the function, then now what happens? Well, A is 10, oh dear, and B is 0, C is 0, D is 0, E is 0. That's because what's happened is we've basically clobbered out all of the other values and replaced everything with just the 10. Now that's not good if we wanted to only change C to 10. So how can we do that? Well, I've written a function here called setPacked, which does exactly that. And what it does is it makes use of bitwise masking and shifting, essentially. And one of the things to bear in mind is that when you take a value and you AND it with all zeros, you end up with a 0. If you AND it with a 1, you'll end up with the same value. And if you OR it with a 0, you end up with the same value. So in a minute, I'll show you why this is important. But these are the facts of bitwise masking that we're going to use in order to achieve our goal. So the thing that we do first of all with setPacked is we pass in a new value. Now notice the value is a uint16, but under the hood, assembly is going to basically treat this as a 32-byte word. So when you pass in a new value of say 10, then assembly is going to see it like this, 32-byte word with a little a at the end there. A represents, of course, 10 in hexadecimal. Then the next thing we want to do, once we've got this new value passed in, is we want to get the old value at the slot that we're interested in. So we're just going to sload from slot C. Now, it doesn't matter which one you use. You could use any of these variables to get the slot number because they're all in the same slot. But this is just an example where we want to focus on changing slot C. The value at C, I should say. So we're going to load in the entire value, which, as you seen just before, is the 32-byte word of all of these values packed together. And we saw that earlier. Now here comes the part where we start to use the bitwise masking that I mentioned earlier. So the first thing we want to do is essentially we want to clear out the value of C from the old value that's stored. So we take the old value and we bitwise AND the old value with this. And what is this doing? Well, you'll notice that it's all Fs except in this position here, where we got these 4 zeros. This is the position of the value of C. This is the 16 bits of data that we want to zero out or clear out using this bitwise masking here. So let me explain. If we take the old value here, which is this, which we just basically loaded from the contract, and we take the mask, which is this, which we've hard coded, which is fine because we know exactly where we want to change the value. And if we use this fact that if we AND with zeros, we get 0, and if we AND with ones, we get the value, then what this means is everywhere there's an F, we're ANDing with 1. So that means we preserve the value. So here, these 4 Fs preserve the original value. So you can see the 02, 03 is preserved. Now the next part here is, remember, is the value of C, which we're interested in. And that gets cleared out because we're ANDing this with zeros. So that gets cleared out. Now the rest of the values are preserved because the rest of the mask are all Fs or all ones. So we preserve these values. 7 and 9 are preserved. So now we've got a cleared value that we can work with. Essentially, it's the same as what's in the contract, the same as what's in slot 3, but with the value of C cleared out. Now, the next thing we want to do is we want to take the new value that we've passed in, which looks like this, and we want to shift left a multiple of the offset where C is. In other words, we want to move the value A that's right at the end into the same position where C is, which is essentially the offset of C. Now we know that the offset of C is 28, so we could hard code that, but in this case I'm explicitly multiplying this by 8. So we multiply the 28 bytes that C is offset by, multiply that by 8 to get the number of bits to shift left, and then we apply that to the new value. So what happens is we get shifted looking like this. Shifted is basically the new value that we passed in, which remember is 10, it has the A on the end, and that A has been shifted 28 bytes over to the left such that its position is now right here. And what do you notice? Well, it's the position of C. In fact, we can see this more clearly in the next line. So what we do to finish this task off is to use an OR, bitwise OR, between the shifted value and the cleared value. And remember, when we OR with 0, we keep the value. So what does that mean? It means that we're able to take the shifted value, which basically is the new value in the position of C, and we OR it with the cleared value of the slot 3, where C has been cleared out, and we OR these two together, we end up with the new value that we want. In other words, we end up with the cleared value of C, or the cleared value of slot 3 that doesn't have C in it, combined with this new value of C. So we get all the preserved values, all the variables A, B, D, and E are still there, plus C has been replaced with the new value here, A, which is 10. And that just leaves one last thing to do, which is to use SStore at the same slot with the new value. And that's it. That's how we can use bitwise masking and shifting to update a specific value that is packed in a single slot. So let's deploy the contract and just test this out. So remember, we've got A, B, and C, and D, and E, like this. Let's change the value. So we're going to change the value to 10, and we click the transaction there, and then we go to C, and C is now 10. And let's just make sure that A and B and D and E are still the same. So that's how you can use Yawl and bitwise masking and shifting to set a value in assembly.